Hello. In this video called Limits Part 4, we're going to keep looking at limits and we're going to look at what are called infinity limits. So let's try the following limit. Let's say we had x approaching 0 of 1 over x squared. Now if you were to plug this in, of course, you would get 1 over 0 and that's undefined. So we can't plug it in, but let's see if we can approach 0 by getting closer and closer. So 0.1, if we do 1 divided by 0.1 squared, you can try that on a calculator, you should get 100. If you do 1 over 0.01 squared, you should get 10,000. In the next one, you actually get 1 million. Now if you plug in 0, of course, you get undefined. If you plug in negative 0.1, well, the negative squares away and you get 100 again. And the other numbers are the same, 10,000 and a million. So let's look here. As x is approaching 0, as x is getting closer and closer to 0, it appears like these values are getting, well, they're going somewhere. They're getting closer and closer to something, but not a particular number. It's not as though they're getting closer and closer to the number 7 or the number 2 or the number 100, but they are doing something similar. These values and these values are both approaching, in some ways, infinity. Infinity is not really a number, so we have to be a little bit careful here. And so technically we could say that the limit x approaches 0 of 1 over x squared does not exist. Because on one hand, it's not approaching a number like 2. It's not getting closer and closer to a specific value. But it is doing something interesting. And so we can be more specific than saying it doesn't exist. And in particular, we can talk about this idea of approaching infinity. So the values here, these values of fx, they can be made arbitrarily large. We can make them as large as we please by taking x sufficiently close to a but not equal to a. And so in that case, when that happens, we say that the limit x approaches 0 of 1 over x squared equals infinity. Again, it's a little bit weird here because infinity is not a number, but what we're saying when we write this statement is that the values of x are getting arbitrarily large. Now, let's try this one here. We've got the limit x approaching negative 2 of 1 over x plus 2 squared. Well, we could try the method, of course, of using a table of values, but instead we're going to use our good friend the sign diagram. So we're going to draw our sign diagram. It's undefined at negative 2, which is an even power. Now we pick a number bigger than negative 2, say 10. When we plug it in here, we're going to get 10 plus 2 squared. That's going to be positive. So it's positive on this side and positive on this side. So what that means is that the graph of this function is always going to be above the x-axis, it's positive values. And then when you get to negative 2, it's undefined. What that looks like on a graph, if you were to go ahead and graph this, is that over at negative 2, you actually have a vertical asymptote. And the graph is doing one of these, where it's approaching the vertical asymptote, kind of like a geyser going up on both sides. And so visually what that means is that the graph is going as high as it can go. It just keeps going higher and higher and higher. It goes up and never stops. It gets arbitrarily large. So we could write that as a limit. This equals positive infinity. Now, sometimes, of course, you might get negative infinity, and this next example will show you that. Here we have x approaching 0 of negative 1 over x to the power of 4. So again, we can draw our sign diagram. Over at 0, it's undefined. Even power. If you pick a number bigger than 0, say 10, it's going to be negative, so negative, negative, which means as a graph, it's always below the x-axis. And so it's one of these infinitely deep wells that you might have seen from pre-cal. And the limit would equal negative infinity. Now, let's not do x squared. Let's just do 1 over x. Hopefully you remember this function from pre-cal. Looks something like this. You got the swoosh over here, and then a swoosh over here. If we start plugging in values into a calculator, 1 over 0.1 will be 10. then 100, and then 1,000. 0 will be undefined. Negative 0.1 will be negative 10, negative 100, and negative 1,000. Now if you notice here, as we get closer and closer to 0, these values are not getting to the same value. These ones are getting larger and larger and larger. These ones are getting, well, more and more and more negative. In fact, these values couldn't be getting further from each other. If you look at the graph, as you go on the one side, it's going out to positive infinity, but the other side's going to negative infinity. So overall, in this case, the limit right here, this limit does not exist. And it doesn't even equal a positive or negative infinity. It just straight does not exist. There's no way we could get a limit for this function because it's not going to some value. They're not both getting arbitrarily large. One is getting arbitrarily large and one is getting arbitrarily small, or arbitrarily negative. And so what we would actually have to say is we have left and right limits. As we approach from the left, the limit as x approaches 0 from the left of 1 over x, that's going to give us negative infinity. But the limit as x approaches 0 from the right of 1 over x, that's going to give us positive infinity. And so these two are not equal. So therefore, the overall limit as x approaches 0 of 1 over x does not exist. Same idea that we've done before. The overall limit does not exist, but in this case, the one-sided limits will. And this is what we're going to look at time and time again when we do some of these ones for infinity, is we're going to often have just a one-sided limit because sometimes the one side goes to negative infinity, sometimes the other side goes to positive infinity. So we tend to investigate just the one side or the other side to get a type of infinity. So let's consider 1 over x minus 5 to the 3. The limit process is as follows. You first draw a sign diagram. So over at 5, it's undefined. Then it's going to be positive, negative, which means the graph looks like this. You can draw yourself a little asymptote over at x equals to 5. It's going to be positive on the one side, negative on the other side. And then the limits, as x approaches 5 from the left, you can clearly see it's negative infinity. And here it's positive infinity. Of course, here, the limit as x approaches x approaches positive 5. The overall limit, not going from the left or from the right, just the overall limit does not exist because negative infinity and positive infinity are not equal. Now, we could do this in general for any power. If you have 1 over x minus a to the n, these all look the same. Just because it was 5 or 3, those are just particular values. Anytime you have 1 over x minus a to the n, they're all going to look the same, where n is going to be an odd positive integer. So here we have a. You pick a number bigger than a, say 2a. It's going to be positive here and negative here. You're going to have an asymptote over at x equals a. It's positive on this side, negative on this side. The limit when you go from the left-hand side looks like negative infinity, and the limit on the right-hand side is positive infinity. Now, when you do all these questions, you just want to be aware that this is the general makeup of them. You still want to, of course, always draw a sign diagram so you can be sure what's going on, but this is what you have as a general rule. If you're looking at just 1 over x minus something to an odd power, you know you're going to get either a negative infinity on the left side or a positive infinity on the right side. Now, just for completeness, if n was even, if you had an even power, well, then your sign diagram would look like this. Here would be your a. Since it would be even, you'd get positive, positive. And so your limits would both be positive infinity on either side. So that's just some general information there. It should help you as you start to look at some of these limits. But again, the usual technique is to always draw a sign diagram, and then you can figure out whether it's positive or negative based on the sign diagram. So let's look at some examples here. We have the limit x approaching 4 from the right of 1 over x minus 4 to the power of 3. So let's draw a sign diagram. We've got 4, positive and negative, Well, we're approaching 4 from the right, which means we're going to be on the right-hand side of 4. That means we're taking this portion here, so we get positive infinity. Let's try the next one here. We've got x approaching 9 from the left, so we draw our sign diagram. Pick a number bigger than 9, say 10, positive, negative. Here we're approaching 9 from the left, which means we're going to take this portion here, so we get negative infinity. Now, you might be wondering, well, how do you know to draw a sign diagram and not to use like a piecewise function or something like that? How do you know that the sign diagram is the technique to use on these limits? Well, I'm going to give you something to think about, but please don't ever write this down. This is just something that you want to think about. Here's what you can think. When you're plugging it into these limits, and you can always try to plug it in first, on the top you have a 1, and on the bottom you're going to have 9 minus 9, so 0. So you're going to have 1 over 0, and it doesn't have to be 1, it could be like 2 or 3, but you have 1 over 0, a number over 0. When you get 1 over 0, what you want to think is that this becomes a positive or negative infinity. Now, again, you should never write 1 over 0 equals infinity because we know that you can't divide by 0. It's impossible to divide by 0. But what you can kind of think is that if you were to divide by 0, if you put a 0 on the bottom of a fraction, what that gives you is it gives you a plus or minus infinity. It's not a do more work type question. 0 over 0 is do more work. 1 over 0 is a type of infinity, and you figure out which type by drawing the sign diagram. So let's look here. Again, we try to plug it in. 5 minus 5, oh, that's a 0 on the bottom, but there's a 1 on the top, so sign diagram is going to be our technique. We draw a sign diagram, and we've got undefined at 5. This is an even power. Number bigger than 5, say 10, it's going to be negative, negative. Well, we're approaching 5 from the left, so we're going to get negative infinity. Let's look at this next question here. We have fx is 2x plus 3 over x minus 1 cubed, x plus 4. We want to do x approaching 1 from the left and 1 from the right. Well, if we were to plug it in, if we plug in the number 1, the top's going to give you 5, and the bottom's going to give you, well, 0 times 5, so 0 on the bottom. Again, this case here is 5 over 0. That's what we got going on, which is not a 0 over 0, so it's going to be some type of sign diagram. Well, let's go ahead and draw ourselves a little sign diagram over here. And we've got a little bit more work to do because this one has a few more pieces to the sign diagram. You've got the 2x plus 3, which means we've got an actual 0 over here at negative 3 over 2. You've got undefined at 1, and you've got undefined at negative 4. So we have a few more pieces to draw. Now we pick a number bigger than 1, say 10, and we're going to get positive, then negative, positive, negative. So let's go ahead and do our limits. Limit x approaches 1 from the left of 2x plus 3, x minus 1 cubed, x plus 4. Well, as x approaches 1 from the left, 1 from the left means we're looking at this portion right here. So it's going to be negative infinity. And if we do the limit as x approaches 1 from the right of 2x plus 3 over x minus 1 cubed, x plus 4. Now we're going to be looking at the right of 1, so we're going to get positive infinity. Let's try a multiple choice question here. Determine the limit. X is going to approach negative 2 from the left of negative 1 over x plus 2. So go ahead and pause the video and give that a try. Alright, so if we draw a sign diagram, because of course you're going to get a 0 on the bottom and a negative 1 on the top, we have negative 2. Pick a number bigger than negative 2, say 10, you're going to get negative and then positive. So we're going to be looking at x approaching 2 from the left, negative 2 from the left, which is this side here. So the answer is D. Again, it's important to draw the sign diagram because just because we're approaching from the left or just because the number is negative doesn't mean the overall answer is going to be a negative infinity. The sign diagram is always your method to determine whether it's positive or negative. So let's go ahead and try a really complicated one. Here we have our big function and we want to find x approaching negative 3 from the left and the right. Again, notice when you plug in negative 3, you're going to get a 0 on the bottom, but when you plug it in the top, you're going to get 9 minus 15, which is not 0. So the sign diagram method is going to be great for us, and so we can go ahead and draw that sign diagram. Now, of course, we have to fully factor, so this we should write as x times x plus 5. And so when we draw our sign diagram, well, we're going to have x equaling 0 from that x. We're going to have x equal to negative 5. Those are both zeros. We draw them as filled-in dots. Then we're going to have negative 3 and 2, and those are both even. So pick a number bigger than 2, say 10. Positive, 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 positive. So we're going to get positive over here, which makes this positive, negative, negative, positive. All right, so the limit as x approaches negative 3 from the left of fx, well, that's going to be looking at this portion right here, which is negative infinity. And the limit x approaches negative 3 from the right of fx, well, that's going to be looking at this portion here, which is also going to be negative infinity. Now, sometimes these limits where we go from the left or from the right result in strange situations. Sometimes it's a positive infinity, sometimes you need a sign diagram, sometimes you need other techniques, and this is a bit of a strange technique I want to show you for this limit. We have limit x approaching 3 from the left of x minus 3 over the square root of x cubed minus 6x squared plus 9x. And on this one, it's not entirely clear what technique to use. If we plug in the 3, we're going to get a 0 on the top. And when you plug in a 3 on the bottom, you're going to get, well, 3 cubed is 27, minus, well, you're going to get 3 squared is 9 times 6, so that's going to be 54. So 27 minus 54, and then plus another 27. So it's a 0. So this here is actually a 0 over 0 type limit. But it seems strange and kind of out of place because we expect the one-sided limits to give us a positive or negative infinity. But this seems like a do more work limit. And it's, again, one of those situations where we have to be aware that just because we're going from the left or from the right doesn't mean we're going to get a positive or negative infinity. In this case, it looks like we're going to get a number. And to look at it, we're going to try to use a new technique. It's not going to be the technique of rationalizing, because although there is a square root here, rationalizing only works when you have a square root plus or minus something else. This technique is going to be about squaring and square rooting. So what we do is we take the top, the x minus 3, and we say to ourselves it would be nice if that was part of a root. Well, I could square root x minus 3, but that wouldn't be equal. Now, if I squared it, you might be tempted to say those are equal. X minus 3 and the square root of x minus 3 squared. But remember, when you square a square root, you technically have an absolute value going on, or you have a plus or minus business. So do we take the plus or do we take the minus? Well, x is approaching 3 from the left. That means x is taking values less than 3. So if you imagine a little number line here with your 3, x is taking values on the left-hand side of 3. So like 2.5 or 2.9. What happens to the quantity x minus 3 if you plugged in 2.9? Is it going to be positive or negative? Well, this quantity is going to be negative, less than 0, which means we take the negative portion of our square root. That's how we know whether to take the positive or the negative. Okay, so that was a bit of work on the side. How does that help us? Let's go back to our original limit. So we have the limit x approaching 3 from the left, negative square root, x minus 3 all squared, over square root, x cubed minus 6x squared plus 9x. Well, what we have here is a square root on the top and a square root on the bottom. One of the rules of math is that if you have a square root on the top and bottom of a fraction, you can square root the whole thing. And also there's this negative sitting here. The negative is like a constant, and one of the limit laws allows us to take the negative outside. So we'll do that. We'll take the negative outside of the limit, and we're going to square root the whole thing. So x minus 3 squared over x cubed minus 6x squared plus 9x. Now another limit law says that if you have the limit of a root, it's the root of the whole limit. So we can take that square root all the way out and just look at the limit as x approaches 3 from the left of x minus 3 squared over x cubed minus 6x squared plus 9x. Now here's where it gets interesting. I know it looks pretty complicated with the negative and with the square root, but this portion here underneath with the limit, we can do this portion. We can do a little bit of factoring here, and we can probably cancel something, and we can figure out this limit. So don't let the square root bother you. This is actually quite a good situation to be in. So we're going to get negative the square root, limit x approaches 3 from the left. We can factor an x out of each one of those on the bottom. So an x comes out at common, giving you x squared minus 6x plus 9. And then if you think about it, we could factor this. Well, that would be two numbers that multiply to give 9, add to give negative 6. That would be x minus 3 and x minus 3, which of course we could write as x minus 3 squared. Hopefully you're seeing why this is so useful. We'll have negative square root limit, x approaches 3 from the left, x minus 3 squared over x minus 3 squared. We found the thing that we need to cancel. 0 over 0 means we need to do more work, and in this case, the work we had to do was to get this root out of the way of the limit so we could do our cancellation. Well, now we're pretty much home free. We have just negative square root limit x approaches 3 from the left of 1 over x. We can go ahead and plug that in, and that's going to give us 1 over 3. So we have, well, negative the root of 1 over 3. Usually we like to distribute that root again, so we have negative root 1 over root 3, which we could write as negative 1 over root 3. And there's our answer. Again, the technique here is a little bit different than what we did on the other ones. We're not doing a sign diagram because we had 0 over 0, so we had to do more work, not a sign diagram type method where you had a 1 over 0. Now, jumping back to that idea of having a 1 over 0 or having a sign diagram type setup, when you get those positive and negative infinities, that's technically called a vertical asymptote. You've seen vertical asymptotes from pre-cal, but you never actually defined them, you just sort of drew them on the graph, and it's time now to give the actual definition. So a vertical asymptote is a vertical line x equals a, and it's called a vertical asymptote of a function if, as x approaches a from the left, you get plus or minus infinity, or as x approaches a from the right, you get plus or minus infinity. So one of the reasons you couldn't give the definition for this in pre-cal was you'd never seen a limit. But now that you've seen a limit, you know that the vertical asymptote is actually a limit. It's when you get a positive or negative infinity from a limit. Now the most common instance for a vertical asymptote is when f of x is a rational function. The values of x where f is undefined, of course, are called the vertical asymptote. That's where you find your vertical asymptote. And in our context, this is important, in our context, the graph does not cross the vertical asymptote. There are crazy graphs out there where you can cross vertical asymptotes, and I'm going to show you one right now because it's an important concept to be aware of. Let's take a look at this strange looking graph here. If you notice, it's kind of got a bit of a wiggle to it. It's almost a sine graph, and as you get closer and closer to the x-axis, well, it seems to wiggle in a bit of a strange way. Let's see if we can zoom out a little bit and see what happens as this graph climbs that axis. Well, sure enough, it seems like as we go further and further up, this graph is approaching that y-axis. you could think of as you get closer and closer to 0, it appears that this graph is going to keep going higher and higher and higher. It's going to go all the way up to positive infinity. And indeed, you could draw a line here and call this a vertical asymptote. It would be technically correct. But if you notice, well, if I draw a line that goes as x equals 0, well, that vertical asymptote is crossing all over the place. It's crossing infinitely many times. And it's important because asymptotes are not about crossing or not crossing. In our context, the graph is not going to cross the vertical asymptote. But there's nothing in the definition that says crossing or not crossing. The asymptote is not some magical line that can't be crossed. The asymptote is a limit. And it's important that you understand that as a concept because we're going to look eventually at horizontal asymptotes. And not to spoil anything, but I have a feeling you might be able to cross horizontal asymptotes. Now again, for our course, the graph is not going to cross the vertical asymptote. And the reason, of course, is this graph here is not technically a function. It doesn't pass the vertical line test. So we're only studying functions in this course, and this is not a function, so it will not be part of our course. But in future courses, you'll study things that aren't functions. And you're going to have all sorts of weird functions that may cross vertical asymptotes. Now back to the example here, let's go ahead and look at this function and see if we can find the vertical asymptotes. So we're going to go ahead and say, I think it happens probably at x equals 3. That's where the function is undefined. So I'll draw my sign diagram for 3, positive, negative. I'll do a limit as x approaches 3 from the left of 2x squared plus 5 over x minus 3 cubed. And because I'm going from the left, that's going to give me negative infinity. Then I'm also going to do the limit as x approaches 3 from the right of 2x squared plus 5 over x minus 3 cubed. And that's going to give me, well, looking at the sign diagram over here, positive infinity. And so this tells me that I have a vertical asymptote. Vertical asymptote at x equal to 3. So let's try a multiple choice question here. Which of the following are vertical asymptotes of f of x equals x over absolute value x minus 1? Do you think it's number 1 and 2, 1 and 2 and 3, or 1 and 3? Go ahead and pause the video and give it a try. All right, well, the vertical asymptotes always happen at values where the function is undefined, and in particular, where the denominator is equal to 0. So in this case, if we wanted the denominator equal to 0, you could try plugging in x equal to 1. 1 minus 1 would give you 0, so that's definitely going to be one of the asymptotes. And if you were to plug in x equal to negative 1, absolute value of negative 1 will be 1. 1 minus 1 is 0. That'll be another one of the asymptotes. So we're looking for the correct answer of B. X equal to 0 would not be an asymptote because if you plug in 0, you'll have 0 over, well, negative 1, which will equal 0. And the function is perfectly defined there. So that will not be a vertical asymptote. So for homework, you can do the one-sided limits worksheet, the limits worksheet parts C, D, and E, and also page 94, number 31 to 41. And as always, thanks for watching.